I should probably do that. So I did not mute myself in the lab. I think today we got recorded because the phone was on mute. That's good. So because of that, I don't have any more instructions that we recorded, and there won't be any video of the lab on Tuesday. So if you have any questions, let me know anyway, because there is no reference back to it. Okay? So we were talking about the other day, we were discussing the problem between traffic flow between origins and destinations, and between O and between one OD pair, right? There was only one OD pair. And we had talked about how we had initially a 2-route problem. And we figured out how do we establish threshold on that 2-route problem. And once we established threshold on the 2-route problem, we could distribute the traffic between 2 routes. Now, we were trying to complicate the problem a little bit by adding a 3rd route to the mix. And this is what that looks like. So all of these 3 routes had what we call the link performance functions that define the travel time T1, T3, this was T3, remember? And this is T2. So travel time T1 and T2, that were my initial routes. And then route T3, which was newly added route. And for all of these routes, I had what I call a link performance function that defined what will be the travel time. So can somebody give me what the travel time is going to be, or what was for T1? T1, T2, and T3 equations.
It was 4 plus 3x1.
4 plus 3x1 for T1. So basically what that tells me is that anytime you add thousands of vehicles per hour, it adds 3 minutes to the travel time on the route. And then the free flow travel time is 4 minutes. And then what was T2?
2.2 plus 6x2.
2.2 plus 6x2, thank you. And then T3 is the newly added route, which I believe was 1.7 plus, no, 5.8 plus 1.7x3. That's right, yeah, 5.8 plus 1.7x3. Now you still had that same 3,800 vehicles per hour traffic flow. So you still want to distribute 3,800 vehicles per hour, VPH, traffic flow, and that's what you want to distribute between the 3 different routes. So now the question again is still the same. How do we define at what point different routes become competitive, and so on and so forth? Was it 5.8? This was 5.8, right? Okay. So how do we go about, like, when now the route problem has become 3-route problem, how do we go about doing that? So what we call, to kind of work out this type of a problem, we have what we call the Lewis rule. Lewis rule is basically an algorithm, a simple algorithm that helps you go and define different thresholds and then solve your problem when you have multiple routes that are potential routes for you to choose from. So what does the Lewis rule look like? Let me go ahead, and I was hoping I could project it, but it looks like I can't. So what I'll do is I'll just define the Lewis rule for that. And if you want to see the Lewis method or Lewis rule, you have that in the slide. So if you want to look that up later on, you have those in the slide. So when we look at the Lewis rule, we start with the travel time that has the worst free flow travel time. Obviously, we're not saying, when we say I start with that route, I'm not saying that I'm going to put traffic in that route first. I'm never actually going to put traffic on the worst free flow travel time route. In fact, my first initial flow will always go to T2, because when there is no traffic on any of these routes, people will pick this route first, because this gets you to destination in only 2.2 minutes. So always will pick this route when people are using it, but the algorithm starts with choosing the route between OD that has the worst free flow travel time. And that route in this case will be T3 or route 3. Okay, so your first step is the ID the route with worst travel time. ID the route with worst Okay, so I'm doing that. And then once I ID that route, yes, I ID the route with the worst free flow travel time. And then, and in this case, that will obviously be X3, route X3. So I'll pick that route. And then for each other route, I'll find the flow rate at which each of these routes will become competitive. Okay, so now tell me, what is the worst free flow travel time that you could have on this network? Worst free flow travel time to start off. T3, and that's 5.8, right? So these two routes, I want to find out at what point these two routes become competitive. Both. I want to find out when both of them will become competitive individually. So find when each of I shouldn't say competitive, because when I'm saying competitive, that basically I'm comparing that to the best route. So I should say as bad as the worst, right? As the worst route. Does that make sense? So what I have here, so your first step is ID the route with worst travel time, and then find the flow rate at which each of the route become as bad as the worst route. Make sense? Right? So let's find that out. Let's take 2 minutes to calculate at what point route 1 becomes as bad as the worst route, worst free flow travel time route. And then at what point route 2 becomes the worst travel time route. Okay, take a minute. Might have to use the calculator if you can. If you don't have it. Okay, so we're taking a minute to calculate the numbers at which each of the routes become as bad as the worst. You have only 2. Yes, please.
So if you're comparing T1 and T3, then you would obviously you would set T1 and T3 equal.
Yeah.
Right?
So see, that's the thing. I'm not actually solving the assignment problem right now. I'm just trying to find the thresholds. Okay. So I won't actually try to equate the travel times or anything like that just yet. I'm just finding out this answer to this question. Find the flow rate at which each of the routes become as bad as the worst route. Okay, and what does that look like for me for T1? It will look like when this becomes 5.8 becomes equal to 4 plus 3x1. So I'll try to solve for this x1. And I'm trying to, when I'm doing this for the second route, I will say 2.2 equal, or sorry, 5.8 equal to 2.2 plus 6x2. Okay. Make sense? And do we have these values of x1 and x2 based on these equations? Do I have the values of x1 and x2 based on these equations? So this should give me something very easily. I don't need a calculator for that. 0.6, right? I probably do need a calculator for this one. How much is that for x2? That's fine. 0.6, right? Okay. So that doesn't have to be equal. Okay, so this is just a coincidence that these numbers came out equal. They don't have to be equal. Now, what do you think should I do? I want to find out. I figured out that this is the route that is at the risk of not being used at all, because people will start going to this one. And then when this becomes competitive with that one, people will start going to that one. And then at some point, the traffic flow would be large enough that folks will say, okay, maybe I need to get on this route as well. So what do you think? What can I do with these two numbers that I've gotten, x1 and x2, to figure out at what point route 3 becomes competitive? What do I do with these two numbers to figure out? Because my goal right now to do these steps is to figure out at what level of total demand between the origin and destination I can put traffic on all 3 routes. Largest value. Okay, so you're saying 0.6?
Yes.
Okay, so that's the one of the responses. Let's just take the largest value. The problem with that is if you take the largest value, which is 0.6, you plug it in here. Okay. So you're saying, okay, so there is the total demand is only 0.6, right? So basically what you're saying is whatever answer you get, you're saying 0.6, that's the total demand. At that total demand though, which route would you use? You'll probably use this one. 0.6 will get us a little bit over this. So I think these two routes will get used at 0.6 travel demand, right? Because I think yesterday we figured out that the big threshold between these two routes were only 0.3. So anything above 0.3 gets us these two routes. Okay. So if the total demand is only 0.6, you can solve the equilibrium problem and you can find the values of x1 and x2. So we know that at 0.6, these two will get used and there will be some split between the two, right? But if there is some split, if x1 and x2 value would be something less than 0.6 in that scenario, right? Maybe it will be 0.5 and 0.1, maybe it'll be 0.4 and 0.2, whatever it is, but it's going to be something less than 0.6 because they're only adding up to 0.6. So I'm following the train of thought and I'm thinking my total answer is the lowest of these values. And since they're both equal, I'm just going to pick any of the 0.6. But what would that do? So if you put in something less than 0.6 here and something less than 0.6 here, what happens? What is the travel time on those routes? It's going to be less than 5.8, right? In that scenario. What does that mean? That means, is this route good enough yet to use? Not yet. So you can't pick the worst of the or the highest of the two answers. That's for sure, because even the highest of the two answers, when you split them between two routes, it won't get you it won't make route 3 competitive just yet. Okay, so that probably that certainly won't work. So what else might work? Yes.
So you add them together.
Adding them together. Yes, that's exactly what it will work. So basically add both of them together because you know that when that's the total flow, when the total demand, so basically what we do is we add them together to find the threshold, the first add them together to find the first threshold. Okay, so what we're doing is we're adding them together to find the first threshold at which all 3 routes will be competitive. Okay. So what is that threshold for me then? 0.6 plus 0.6, 1.2, which is x1 plus x2 should be 1.2. That means anytime my total demand exceeds 1200 vehicles per hour, remember all these units are thousands of vehicles per hour. So anytime my total demand exceeds 1200, then what would happen? What this calculation told me is that anytime my demand exceeds 1.2, what do I have to do? I have to make use of all 3 routes, right? To distribute my traffic, I need to make use of all 3 routes. But anytime my demand is less than 1.2, my traffic will only go to these 2 routes because this route would not yet become competitive. Okay, so this is how you do it. Now, but your total demand was given to you as 3,800. So then you just solve. Basically, you know now that all 3 routes are going to be used. But now you know how to solve the problem. Whether it's a 3-route, 2-route problem, it doesn't matter. It's just going to be a little bit more calculations because now you have to solve more equations. But essentially, you know all 3 routes are being used at this demand level. So you need to come up with 3 equations and then solve those equations for x1, x2, and x3. Okay, so let's see if we can do that here. Okay, so again, Lewis rule is on your slides, so you can look that up later. So once I do that, I need to come up with the 3 equations. So I'm going to write those down. My first equation will be conservation of flow. So I know x1 plus x2 plus x3 is equal to what? 3.8, right? 3,800, but because these are being measured in thousands of vehicles per hour, I stick with 3.8. Okay, and then I need 2 more equations, and I can get those by saying T1 equal to T2 and T2 equal to T3. Right, so I can use those equations. T1 equal to T2 will give me 4 plus 3x1 equal to 2.2 plus 6x2. And T2 equal to T3 will give me 2.2 plus 6x2 equal to 4 plus 3x1. Oh, no, the same thing. So I need an independent one. Yeah. 1.7. Yeah. Questions about this? Yes, please. Yes, yes. So you could have done, you only had to pick 2. So you could have done this T1 equal to T3 as well. You could have done 4 plus 3x1 equal to 5.8 plus 1.7x3. But there is a little wrinkle to this. Yes, you could have done this, but now I have 4 equations. Can I pick any 3? I can't quite pick any of these 3. I have to pick this one and then any 2 between those. Because remember, these 3 are not independent equations. When I have 3 unknowns, I need 3 independent equations. And these are not necessarily independent, because even if I take this out, say T1 equal to T2 and T2 equal to T3, automatically means that T1 is equal to T3. So definitely pick one, the conservation of flow equation you have to pick. And then out of these, pick any. Yeah. Okay. Now your homework problem actually is a 5-route problem. Okay, so this is basically, it's the same thing. You will extend the same thing, but there is one wrinkle to it, is that you have to solve multiple problems like this. So in this case, because our total demand was more than 3,800, we could straight away say that, yeah, these 2 routes won't suffice. All 3 routes would have to be used. And then I could solve that 3 route 3. And then I'm not solving these equations, of course. I'm going to let you figure that out, how to solve these equations. Okay, so 3 equations, 3 unknown, should be able to solve. But if you have a 5-route problem or anything beyond that, or even in this problem, what if my total demand was not 3,800? What if my total demand was, I'm going to change this demand now, not 3,800, but 800 vehicles per hour. If you can solve this problem, then you can pretty much solve your 5-route problem. What's the big difference?
Can you just say that route 3 is not going to be used?
Yes, you can say that, definitely. Yeah, because 800 vehicles per hour is less than 1,200 vehicles per hour. You could say that at this point, route 3 won't be used. But that's a different thing than saying that route 1 and 2 both are going to be used. You see the distinction between the 2 terms, the 2 statements that I just made? At 800 vehicles per hour, you can surely say, you can 100% say, just by looking at just these equations and numbers, I can say route 3 won't be used. But I cannot yet say, at least just by looking at what I have going on right now today, I cannot yet say that these two routes will be used. It's possible, theoretically, it's possible that only one route gets used. So I still have to figure out the same threshold among the remaining routes. So basically, when you do these numbers, you're not able to ascertain how many routes will be used. You'll only be able to ascertain if the worst route will get used or not. You see the difference between the two statements again? You cannot say just by these numbers how many routes will be used. You'll only say whether or not the worst gets used or not. Okay, and if you understand that distinction, when you have a 5-route problem, you start with the worst and see if you can eliminate that. Okay, if you can eliminate that, discard that one, and now figure out the next worst route. And then repeat the problem until you finally figure out. In this problem, it was easy because 1.2 was lower than 3800. So we could say that, yes, all three will be used. I'm done. I mean, I can proceed to solving this conservation of flow and this user equilibrium problem. However, when I don't have that going on for me, when at 0.8, for example, at 800 vehicles per hour demand, I couldn't quite say that. So how do you think we should go then? We should eliminate route 3 from consideration in this case, because 800 is obviously less than 1200. So I'll eliminate route 3 from consideration, and I'll do the same thing, which is the worst route. Now it's only a 2-route problem, so it's easy now. And we solved that problem yesterday, right? And we'll repeat that problem. But even if it's a 5-route problem, I will just systematically go do the same thing. So I want you to try that for your homework. Okay, so let's try that. Come back and see if we can, see where we get hung up or what happens, and we can talk more about it. But it's the same problem, but I want you to think about it a little bit independent of what. So basically, just kind of trying to extrapolate what you learned from here to that 5-route problem. Yes, please. Not 2 equations. It could be that 4 routes get used. I don't know how many equations. It could be that 4 routes get used, or maybe only 2 get used. Only if only 1 gets used. Depends on the total demand and what's going on with different routes. So we can probably Okay, so I have that route problem. So let me at least write that problem down and see if that makes sense. I have my route problem here. I'll try to write that 5-route problem, okay? Maybe we can talk about it for 1 minute. I want you to and again, this is all recorded, so don't worry about it. So I got 5-route problem now. My 5-route problem says T1 equal to 18 plus 4.5x1. T2 equal to 21, 26, 29, 34, 29, 26. Plus 7x2 plus 4.9, 3.4, 4.9x3, 3.4x4, and 0.3x5. So this is the problem you got going on. I got five travel time, 5 link performance functions. And it says my total demand is 8,300 vehicles per hour. Now I won't straight away, definitely I will not do that. I will not go straight away to then figure out, brute force and 5 equations, 5 unknown. I won't start with x1 plus x2 plus x3, x4, x5 equal to 8.3. I will not start there, because what will happen is that it might work, but it might give you some absurd numbers and then you would have wasted all your time. So that's not how you start. You start by thinking about which route is at the risk of not being used, right? Which is this one. Okay. And then you figure out at what point the travel time becomes 34 here. At what point travel time becomes 34 on this route, and then on this route. And then I'll find X1, X2, X3, and X4, add them up, compare them to 8300 or 8.3 to see if I can eliminate route 5 completely. If my number comes out to be less than 8.3, I add up these four, right? So that means that route 5 will become competitive by 8.3 at that demand level. Right? Then I have 5 equations, 5 unknown problems. But it's possible that it comes out less than 8.3. I mean, the total comes out to be, the total comes out to be less than 8.3. And then at that point, I will say, okay, it looks like I can eliminate route 5. But I'm sorry, I said the other way. If the total comes out to be more than 8.3, right? If the total comes out to be higher than 8.3, then I can say 8.3 is not high enough demand to make the route 5 competitive. So I will eliminate route 5. And then I will assume that I have a new problem that only consisted of these 4 routes. And then I will repeat that process with T4 or route 4. Make sense? And I'll keep doing it until I know for a fact how many routes are getting used. Each step only eliminates one route. It doesn't ascertain how many routes get used. Okay, that's the key difference. That's the statement you have to remember. So work on it. Let me know what happens. Hopefully we can get that homework problem done. Okay. One thing I want to talk about a little bit about, it's very interesting what happens when you have this user equilibrium, and because people are trying to minimize their own travel time, sometimes it leads to results that may seem counterintuitive in nature. And that's what the Braess's paradox is about. Okay, that's what Braess's paradox is about. And I want to quickly show you an example of that. And then I have a little YouTube video that I can share with you in the lab today, which actually demonstrate that this actually works in the real world as well. So let me get started on the idea of the Braess's paradox, and as I said, that works in the real world situations as well. So let's say you have this origin and destination, and you have sort of these links in the middle. And then there are let's say there are these nodes here that exist. Maybe let's call them point A and point B. So they are sort of midpoints of the route. And these links have their own sort of link performance functions. Okay. So travel time on this link is T divided by 100, capital T divided by 100, where capital T, and let's call it X because that's what we're using, X divided by 100. X is the flow on each route. And then on this link also, the travel time is X divided by 100. So you can think of these links. What is going on with these links? They have no free flow travel time. So when nobody is there, you can just basically instantaneously pass through that link. But then when there are people, then it starts to take some time and so forth. So you can think of these as like maybe a gate or a toll plaza of some sort. Okay? So the travel time is 0 when nobody's there. But when somebody's there, then travel time is how many people are there divided by 100. Okay. And then the travel time on these links is always 45 minutes. Travel time on these 2 links is always 45 minutes. So just a theoretical, simple network example. So if you look at the overall routes, the first route and the second route, you can say the travel time of route 1, which is route OAD, travel time on route OAD is you can add these to travel time, right? X to X OAD divided by 100 plus 45. And T OBD. So I'm writing these link performance functions right now. The travel time on link OBD would be 45 plus the OBD subscript stands for the specific route, OBD or OAD, right? Yes. Yeah, so this is the thing, right? Like, there is conservation of flow, right? So anybody who starts to go down this path, this is the only path they got. So yeah, so whatever. Now the good news is that this travel time is it's only always 45. So now you might be thinking like, okay, it's completely unrealistic, but it's not as unrealistic as you might think, right? Because we have roads like freeways, for example. The travel time on those freeways does not change until you get to like maybe 1,300 passenger cars per hour per lane. So you remember that our old highway capacity manual flow speed curves, where the speed doesn't start to go down and the curve is almost flat until you hit 1,300 vehicles or passenger cars per hour per lane threshold. So you can think of this as that way a little bit, is that the demand is never high enough to budge the travel time over here. The demand is never high enough to budge the travel time over here. The travel time on these links always remain 45. And these are your toll plaza gates of some kind, where you can just pass through them without any time. But if there are people, you have to wait for a certain time. Okay, so this is sort of the setup of the network. Now you can probably see whatever the demand is, how that demand will distribute between the two links. The free flow travel time is the same on both routes. You can probably think of what happens in this network if you have, and let's say x is in number of or flow rate, the direct flow rate. So let's kind of start off with saying that there is let's start with some certain demand level. Let's start with like 5,000 vehicles per hour. Let's say the 5,000 vehicles per hour want to go from the origin to destination. How would you distribute that demand between these two routes? How would you distribute it? Yeah, it'll evenly split it because both routes become competitive at the same time. Because their free flow travel time is the same, 45 units of time. So whatever demand you pick, they're going to always split even. Okay. So now let's think about is that you made some infrastructure changes here, and you somehow what you did was you added this third link in there. And these are all sort of one-way links, okay? So you can only go towards the destination. You added a link here, and this link is so fantastic. This link is so wonderful that it doesn't even take any travel time. You can just sort of jump directly through it. It doesn't even matter. Zero travel time link has been added to the network. Now, how many routes you have, first of all, to go to your destination? These are all one-way links. So this one goes this way. It doesn't take any time. So how many potential routes do you have? No, this link only goes one way. 3 routes now, right? So you have the OAD, you still have that. You have the OBD, but you have a third route now, which is T, I'm going to define that with OABD. And what's the link performance function for that route? The link performance function for that route.
X over.
Yeah, so basically X, O, A, B, D, whatever traffic flow is taking that route, times 2. Okay, because you're going to use this route. So X, O, A, B, D by 100, and then no time here, and then X, O, A, B, D over 100. So yeah, so that's a good point. So basically, the concern is that, you know, so it won't actually, so it doesn't always have to be the same. But you're right. So yeah, it could be that there might be traffic that goes here that, you know, that affects it. So probably I shouldn't say 2XOABD because that might be a different flow rate. But I should probably say XOA, whatever travel time, whatever flow is on this link, plus XBD divided by 100. So that's right. So yeah, so these don't have to be the same. That's a great point. Is that, you know, these things might be different. But one thing to remember is that, so when you are the first driver, where do you start? You always start here, right? You always take this route because this avoids that 45-minute of free flow travel time. So this route is always the best free flow travel time route. The question is, and then in this case, you don't even have to worry about OA and BD being different because if this is the route you're taking, you always keep taking that route, and then OA and BD will always be equal to, at the beginning at least, right? Until all three routes begin. So what happens when do you think the other routes come into play at all? So you keep going there, and then OA equal to BD, so you can actually have a certain flow. But now you want to think about, so let's say the total free flow is 5,000. Is that 5,000? Do all routes become competitive at 5,000 flow? So 5,000, this will be 5,000 divided by 100, which is what? 50 plus 50, that's 100 minutes of travel time, right? So that's 100 minutes of travel time. So at that point, it looks like these routes should be competitive. But what if the demand is only 2,000? What if the demand is only 2,000? 2,000 divided by 100 gives you 20. 2,000 divided by 100 gives you 20 again. So that's your travel time of 40 minutes. So all 2,000 vehicles per hour will always keep taking this route. So what if the demand was at the 20? Yeah. So basically what I'm trying to say here is that, and then for the 2,000 vehicles per hour, what was the travel time before? It looks like in this scenario, you're better off, right? So you are better off with this new route. But okay, so I need to come up with a number that, so what I'm trying to say here is that there are numbers, there might be scenarios of total demand. There are scenarios of total demand at which you might actually be worse off in terms of aggregate travel time having this link in there. Having this link in there makes the travel time worse off. And maybe I need to adjust the free flow travel time on these routes, depending upon the free flow travel time. So in this scenario, at 2,000 vehicles per hour, I get 2,000 divided by 120 plus 20, 40 minutes. So I'm probably still better off than what I used to be. And then maybe at 4,000, what happened at 4,000? 4,000 divided by 100. Yeah, actually, if you think about it, Are you better off or the worse off than before? Is the question. What happens if everybody takes this route? You end up with 4,000. So 2,000. 4,000. What happens? Let's just think about this. 4,000 divided by 100, 40 minutes here, and then 40 minutes here as well. That's your 80 minutes of travel time going from origin to destination. Right? Now think about this. 80 minutes of travel time. But when you did not have this route, what was your travel time in that scenario for everybody? It used to be 45 minutes on this route, and they would have divided them equally. 2,000 divided by 100 would have given you 20. Your total travel time to go from origin to destination was only 65 minutes. So adding a route can sometimes make things worse because sometimes people don't have incentive to switch routes in that scenario. And sort of conversely speaking, sometimes take away routes can leave everybody better off because the way folks divide themselves into. Now, this is a very, very simplistic network, a very, very simplistic example, but they actually tried that in New York City back in 2009, and they took away Broadway, and that actually made things better for the overall network. Travel time actually went down using this type of approach. And what I'll do is I'll stop here right now, but in the lab, I'm going to show you a quick example of how this works and how this actually worked in practice as well. So it's like a 5-minute video that you can watch and figure out. And in the lab today, you'll also have time to wrap up your report, your memo. So you'll have some time to work on it. And then, if I see a lot of folks are sort of done with the memo, I can also assign the next lab where we can start playing around with these. Okay. Thank you very much, folks.